Welcome to Webinar Wednesday. I'm Kevin Corson, the Powder Coating Institute's Executive Director. On behalf of PCI, thank you for joining us for today's webinar on 3D vision and object perception in powder coating, presented by Sam Jurgis and Robert Reisenbergen with Omni Robotic. Before we get started, I would like to remind everyone that all attendees are on mute, so if you have any questions along the way, please type them in the questions panel. The speakers will address the questions at the end of the webinar. If we run out of time, there will be contact information on a closing slide, and PCI will respond to you directly with any additional questions. This webinar is being recorded and will be available through the PCI store within 2 business days. All attendees will receive a brief survey after the webinar. Please take a few moments and reply to the survey. We appreciate your feedback as PCI continues to develop new programs to offer the topics and training you need. Now I'd like to introduce the presenters for today's webinar. Robert is the Marketing Director at Omni Robotics. He has nearly a decade of experience in SAS and AI-based automation. He helps bring new products to market and enables partners and end users to understand how they can generate a maximum value from the most critical investments. Sam is the Business Developer Manager at Omni Robotics. He has over 20 years of experience in robotic industry sales and integration. His automation experience has guided Omni Robotics partners and customers to better outcomes. Sam and Robert, thank you for being here today, and I'll now turn it over to you.
Thanks so much, Kevin, and thanks to everybody in attendance. Seems like we have a great turnout. So the topic of this presentation is 3D vision and object perception in powder coating. So we'll do a bit of an overview of kind of the state of the industry or the state of the art. What we primarily work on as it pertains to spray processes, but also the implications of that for robotics overall. As Kevin said, I'm Rob and I'm with Sam. We'll go with one camera for now, but Sam will jump on once the Q&A starts. My background is so SaaS, usually pronounced SaaS, but software as a service. So really focused on bringing software into new environments and providing a service model where there's less to worry about. There's more benefits in the long run, and with iterative capabilities, you're not stuck with a system you get out of the box. You get something that can evolve. Sam, maybe you just want to speak a little bit.
Thank you, Robert. So Sam Jurgis, I don't have much more to say. The introduction was pretty accurate. So many years in robotics and industrial automation. I've joined Omni Robotic, I think now 2.5 years ago, and the main reason is that I was amazed by this technology. Being myself a former robot programmer and spend hours and hours trying to figure out the robot programs for all kinds of different parts that I needed, whether to paint, glue, or do any kinds of process. I know how difficult these robotic projects can be, and knowing now that we can finally use AI to basically overcome this challenge, it's for me it's really impressive, and yeah, that's why I want to, as much as possible, bring this great technology to the market, and I know the market is looking for this. What I've been hearing about labor shortage and quality issues and consumable prices going up as well. So yeah, robot is the way to go, and I think AI with robotics now is the solution. So enough about me. Go ahead, Rob.
Thank you, Sam. So I'll go ahead and dive right in. Really, some of the topics we want to go over is just understand kind of the total landscape of 3D vision. Understand where robot autonomy, so not just robotic automation, but autonomy makes a big difference, and then some of the novel techniques that mesh with that, and then understanding the impact of not just having the right hardware, but also the right software. So really bringing more and more value on the software level, almost the same way that your smartphone camera these days, a lot of the features are based on software and not strictly on the hardware or the sensors used. but a mixed approach that produces a better and more variable result. Now, firstly, understanding why things matter, it's a big deal. So if you're looking for a new level of automation in a powder system, or particularly if you're looking for a vision system to help drive more and more powder and more material through your booth, there's a few reasons that you're gonna look for a solution like that. One, chief among everybody's mind is the skilled labor shortage. And things are looking up in the industrial space, but the skilled labor shortage is a big blocker to really reaching the order level and output that people are looking for, and particularly the quality as well. Because if you bring on people who are just new to the line or new to the job, that could be more costly than is beneficial, right? Because you don't necessarily know what their skills capacity is. You might train them and then they move on 3 months later. You might have a variety of things happen that just kill any ROI there. Then, in terms of looking for automation in powder, you may have in a high mix environment, you may have a lot of different batch changes. You may have batch sizes all the way down to one. We were recently at FabTech. I think one manufacturer I spoke to, or one custom coder, he said he probably works on about 300,000 SKUs in a year. That's not a situation where if the shapes are significantly varied, if there's a lot of changeover, traditional automation could really meet the need. Then, with existing automation systems on the margins, there is a challenge of rework, touch up, and rejections. So whether that's with manual, where you'll have a much higher frequency of that, just because humans are prone to error, humans can only do so much work in a given day, or you're using an automation system that doesn't necessarily match all the needs of the parts or the process objectives you're trying to meet. That's where thinking about a new way to automate is important. And strictly speaking, there's a lot that's been accomplished, but the existing vision systems that support that aren't necessarily up to the task all on their own. So how do we think about machine vision overall? There's a few kind of traditional responses at this point, that have emerged over the last 20 or 30 years. There's 2D scanning. Now, this is very often useful for picking applications. There's laser positioning, there's infrared. These kind of camera systems will offer a little more accuracy and maybe a little more depth, but they don't necessarily tie to an autonomously generated output or something that is as responsive as most coders will need, or as most coding lines will need to really exceed their current output. And then there's 3D digitization. So in this context, a lot of manufacturers will digitize a part, will maybe mix in use of 3D CAD files or other formats to drive either the positioning of an existing automation system, or you could generate a robot program about it, around it. But all of that is generally not happening in real time, which means it rules out, the 80% or 90% of manufacturers that are working in a high mix mode where there is a lot of changeover, there is a lot of batch variation, and hence, automation continues to be limited or very fixed and specific. Now, if we think about relating those vision systems to what's really used in powder coating thus far, primarily in automated booths, you'll have light screens or laser positioning, and you'll also have reciprocating arms responding to the relative position of parts or of the depth of parts on 2 or 3 axes. Now, that can generally lead to some challenges in terms of Faraday caging, in terms of kind of regular touch-up spots, and usually there is some kind of pattern there. And in that context, the output per dollar you achieve there can't really be matched. I mean, the systems today are so effective and so efficient that you're not going to, why try to fix it if it's not broke? But at the same time, there are exceptions, there are edge cases, there are all these things that add to a need for more capacity, or a need to add touch-up or manual labor to complement the robustness of existing automation systems. And that's where we get to matching the human eye to that. You get people going into a powder booth, if it's hot, if there's other constraints, they have to wear all this protective equipment. They're obviously covering their eyes to a certain extent, and there are ways to maximize process reliability, but human error can always creep in. It's a tough job. It's difficult to get people to do it, and it's especially difficult to get people to do it well, but it needs to be done. So how can automation take the next step? Sam, maybe, would you have anything to add in terms of the light screens or in terms of some of the other vision systems you've seen in the past?
No, I mean, you've pretty much said it. Those systems will provide a really good throughput, but the fact that one of the reasons why is that they have to control less axis, maybe one or two axis. And if I'm thinking about the reciprocating arms, they will run over one or two axes. So it's a semi-flexible automation solution. So less access to controls, control depending on on one or two sensing feedback. This really returns a really great speed and output. However, as you said, it's not as flexible as controlling a 6-axis robots, but then you have more axes, then you need more information to control those axes and to adapt to the different situations like you mentioned. So, and therefore, that's why our technology fits very well with 6-axis robots for these applications.
Thank you so much, and I appreciate you bringing up the 2 or 3 axes versus 6, because if we think about how do you match the motility or the movement of a human arm, a robotic arm, is the best proxy for that. But there's a challenge with robots, and punchline slide. But what's the real problem is most robotic systems, you expect very large volume, very large batches, everything's jigged or fixtured in some very precise way. And for most coders, if you're hanging something on a conveyor, if you're working in even a batch booth with racks with different parts, whatever the workflow is not typically what's going to match today's existing robotic approaches. So there has been some progress around this. It's not strictly a lost cause. Traditional robot programming companies and robot vendors are finding ways to make it cheaper and easier and more accessible. Now, primarily where that's benefiting people is really in machine tending, where there is still a relatively high amount of volume and a very simple task that doesn't have a fine quality output. I mean, you're picking up a part, you're placing the machine does its job, cycle runs, pick up the part and put it aside, put in the next part. That's not the same degree of complexity or the same degree of risk as actually trying to code something, right? Then, in other contexts, you can do human-machine interfaces. So this is very commonly found in, kind of low programming approaches, but not strictly no programming approaches to robotics, because basically you still have a user interface that can work with an operator who is not a skilled roboticist or not even, an engineer. And they'll be able to understand how the system works, understand the limitations, understand what parts are going to be processed, but don't necessarily have the ability to step outside of the limitations of the system. Now, it's important to understand that the limitations of the system are there for a reason, because they make what the system is good at possible. But it still has those limitations in terms of, at some point, a roboticist needed to touch it in order to generate that output. The robots aren't necessarily functioning with as much autonomy as they could. Now, here is where we like to make the point about what is an autonomous robot and what is really the value of this. So MIT defines these robots as intelligent machines. They're capable of performing tasks in the real world without explicit human control. So that means that as they generate a plan, and kind of execute all the aspects of a process, a human doesn't have to guide that. A human only has to set the goals or set some instructions, some process parameters, some constraints, and the robot can execute within a broad set of goals rather than narrowly defined specific geometries that you'd find, either within robot programming or underlying what's in an HMI. And then, of course, if you have a particular instance of an autonomous robot, you can throw an HMI on top of that to make it easier for an operator. But that whole value chain is still there, and it's much easier to get to in the long run than trying to replicate the process of, strictly HMI-driven machines for every single shop, that really needs it. So, on the vision level, what step is required? Basically, the approach we use, we call it 3D perception, involves infrared depth scanners combined in an array. So you can see that in the GIF here, and then you can see parts passing through. And this is basically what the scanners see. So, depending on the color hue, that indicates the distance from the scan. And then all those scanners together in their multiple positions are using a technique called sensor fusion. So that came along in about 2012, and that was part of the inspiration of Omnirobotics founding, in fact. But that technique allows for a real-time 3D rendering that can be then processed in a digital twin that allows a robot program to be generated autonomously instead of relying on sort of HMI-driven constraints or program-specific or geometry-specific constraints that come with the way things have been tried in the past. Now, this can reconstruct full objects. You can see some of the fidelity there in the lower GIF, and works with static or moving parts and compatible with most surface finishes, including bare metal. Now, the only challenges there for certain scanners, obviously, if you have interference with the direct light, if you have a really acute reflectivity, which is generally fairly rare, that kind of interference would mess with almost any kind of scanning system. Now, there's some that are designed specifically for that, but using the depth scanner approach, using infrared, using sensor fusion altogether is generally the most cost-effective and easy to replicate version of this. Now, what is the underlying principle of that sensor fusion? There's not just the sensor inputs that are there. There's also a 3D model that is being contributed to and built upon in the production case. It's a digital twin where that sensor fusion data is injected and then remains at so if you have moving parts within that digital twin, it's almost the same as you would have a self-driving car. Now, what's being animated here is not the car itself, but the robot, right? So that robot is responding to the changing position, the changing variables, the changing shape or requirements around parts, instead of, look, here's a cyclist, I better avoid this person on the road. But fundamentally, it's the same principle as the massive amount of sensors that are being used right now to commercialize self-driving cars. But in this case, it's a more constrained environment than a suburban street or a highway, so it allows for a little bit faster delivery. Now, within this, what's the important capability? You don't have to assume a one-size-fits-all approach, which is very common for a very common interpretation of robot autonomy, right? If you have an HMI-driven machine, you're going to just try to replicate the same thing over and over again, almost with the same frequency or the same intensity that you would see in a traditional robot programming approach. In our case, what we're attempting to provide and how we're attempting to bring this vision system to people is through software and through the capability to incorporate any robot brand. So we support ABB, FANUC, and UR as an example, and then different booth layouts. So whether it's a batch booth, an overhead conveyor, something where you might have 1, 2, 4, 6, theoretically an indefinite number of robots, but obviously per line functionally a certain limitation will always make sense. And then support and model spray processes in a unique and consolidated way. So, understanding how that sausage gets made is important, because basically it's not just the vision system that's adding value in this case, but it's a vision innovation that's complemented by a software basis for autonomizing the robot. So within the AI planning approach that is used from the digital image or the digital rendering of parts, you can also incorporate the digital twin. So the layout, the process model. Do you have standoff? Do you have a certain angle that you want to target? What is the pressure in the gun? Is there a purge protocol to run periodically? Are there kinematic constraints with the robot? Is there a collisionable environment? Could the robot hit walls? Could the robot hit a pillar that otherwise could not be engineered around? And then understanding primitive tasks or goal sets. So what kind of shapes are being processed? How should different shapes in terms of spherical, conical, planar, boxes, all these different aspects have to be built into the software, but then that's a much more generalizable toolkit than saying, I would like to coat a door of different dimensions, or I would like to coat a kitchen cabinet of different dimensions. When you take it to the shape level, you have a lot more durability in terms of how a solution can actually improve the automation of a process. And then goal sets now, there might be ways in which you want to model the thickness that's achieved. You want to test and assess that. That capability exists essentially within this software, and you have to have capability like that in order to actually maximize the value of the vision system and get to the point where you're making the most of the technology available. And all of that is taken into account, organized in a hierarchical fashion, and using AI, using a bunch of different algorithmic techniques that are not strictly deep learning or reinforcement learning or some of the other methods that people may have heard of, but really taking a more distributed and hierarchical approach in order to coordinate each aspect of the process and assemble a consistent and efficient motion, and then use the brand robot driver to then stream out that motion and deliver the output that you're looking for. Now, with vision, strictly scanning and then generating a path of the part is only the beginning, right? So on the software level, you can continue to add value when you have the right vision approach. One of these is a fit to CAD approach. So that's something that can be used when you have a limited number of cameras or positions that you can incorporate. For instance, you can only have cameras on one side, or you have camera position limitations because there's a wall next to your conveyor at a certain point upstream of the booth that you're processing parts in. You can also plan individual parts in advance, just based on a CAD file without needing to scan. You can ensure or maximize the perception of hidden volume. So if you have very deep boxes, if you have very deep cavities that even a vision system will not generally be able to perceive, because let's say there's an enclosed space and there's a cavity behind it, or there's an internal coating that needs to occur, that can be driven with the combined use of a CAD file. And then you can also kind of identify faces. You can identify different components if you have a different process goal, or let's say you want to maximize rust prevention on edges or on different parts, on different segments of a part. That's where combining CAD files with the baseline scan to path generation capabilities are key. Then there's other aspects where you may not need every detail as high fidelity as you might want it. So in this case, we know powder is a forgiving medium. We can consider geometrical semantic representation. So this is a method of smoothing shapes according to the tolerance that you're really looking for. So for instance, in this example here, you have a highly detailed part. It's very large, and if it were in motion, you wouldn't want a robot to spend time doing each and every detail and going over every single aspect of the part. And you know, in a powder context, that you wouldn't necessarily need it to do it because it's electrostatic and you don't necessarily have deep cavities at every point in the part. So smoothing it over and then identifying, for instance, if I want to have a certain angle of attack on cavities that resemble, you know, these portions in the middle, if I want to follow a certain plan or speed, setting those behaviors is critical. And digesting the part on the vision level between the scan and the plan, or the perception and the plan, is another value add that can increase the efficiency of a system like this. And just to give you an idea of the overall layout that would sort of accommodate using a 3D perception type vision system, and then, you know, presumably our technology incorporated with that. You know, you have the vision system upstream, you have parts coming through, you have your booth. Generally, you know, if you're higher output, you want a robot on each side and you want to get parts done all at once before they go into your oven. In this environment, the real kind of action, or the real planning and motion generation and moving on to the next part while a part is being processed and staying ahead of your line, is done by, in this case, our Omnibrain, which essentially houses that AI methodology, those algorithms, and those task planning approaches in order to give you on-site, without latency, that real-time capability to keep spitting robot programs out as the parts come according to their real position and orientation and their actual shape, of course. So in this circumstance, because you have that vision approach, and because that vision approach is using novel techniques, you're able to hang parts, and you don't have a limitation on how you're hanging parts. Obviously, you don't want anything that's going to interfere with the robot or collide with something, or just be impractical. But you know, if something's off 2 inches, it's not going to kill you the way it would with a traditionally programmed robot. It goes in the booth, and as long as the position is consistent between scan and processing, or the relative position is consistent between scan and processing, you don't have, you know, an added challenge of, oh, am I going to have to scrap that part or rework it or whatever it is. So in that circumstance, I think, Kevin, maybe you have a little bit to say about PCT.
Just that everyone on the call here, that Powder Coating Tough is the only magazine in the country that serves the powder coating market. It is available both in print and digital editions. You can go right to the website powdercoating.com and subscribe. It has a lot of good articles, and you know, a lot of good new things that are up and coming, and things that you can apply to your own lives and businesses.
And then I believe you have another announcement right here.
Yes, and for everybody, our Powder Coating Week is all scheduled for March 7th and 9th in Orlando. It will be a 3-day event involving, for Custom Coder Forum, we will have our 101 basic workshop for training, and then 2 days of technical conferences with the latest and greatest, along with supplier exhibits will be present and available for you to talk with vendors and learn what's new. And at this time, yeah, I would ask that anybody, if they have any questions, feel free to type them in now into the question tab that's on the webinar there, and we can have either Rob or Sam answer them for you. There's a question: if someone wanted to see this in action, how would they go about doing that?
I can say in terms of 3D perception, we do have a video that encapsulates the process front to back. We do have a variety of videos, showing actual parts being processed. We have a lab up here that we use for strictly for motion planning, but not for full application. Just not all that hardware set up here in Montreal where we're located. But we're working with partners to set up those full demo facilities, and obviously working with customers to try to expose as much as they're willing to expose, because some are very productive. Sam, maybe you have anything else to add there?
Yeah, I can add that yes. So beside the fact that we have a lab here and we're working with partners to set up real application demos in the U.S. Another thing also to consider is that since it's a very powerful technology, and it's very difficult to reproduce everyone's application in a lab or in a demo setup. What I mean by that is you might have a certain type of powder coating done in your in your facility, but for all kinds of reasons, whether it's a batch type application or whether it's a continuous moving line or stop and go conveyor type, it cannot necessarily be reproduced exactly at the demo level. So what we say to customer, what about you try it yourself? So this is something also we support. We can rent a trial system and then support the customer, with the elaboration or with basically building their own behaviors and try it for themselves, because high mix production has so much variety. We have customers telling us that they have over thousands of different parts, so it's very difficult to validate and see outside of your own production facility. It's not like high volume where that part or those little sample of parts can be tested elsewhere, because that it's going to be the same part doing over and over for the years to come. In the cases of high mix production, really the best way to validate if the technology works is really to try it over your own facility in your production environment. So this is something we can help customers with.
Okay. What's the general system lead time? And I'm sure there's a lead time for the equipment, but there's also a lead time for learning and setting up. And this can be in general. I know it can be specific for different applications, but just in general.
I can answer that question. So on our side, usually the lead time is pretty short. It's usually shorter than the lead time to build the entire system. So we provide, we've been told that we are the enabling technology. We enable the fact that you can install robots to run your powder coating cell. But basically the long pole in the entire project will be to install the robots themselves and do the engineering to get those robots in there, and make sure they work safely, and and all regulations are respected in the engineering and installation. So that typically will take between let's say an average of 6 to 9 months to get done. And that gives us the time, to support the customer through the process of getting familiar with our technology, train the customer, do proof of concept or any kind of validation the customer would want to have, to make sure that when the system is finally installed, we just need to incorporate and integrate our Omnibrain, and the users are ready to go as soon as possible.
Okay. Question is could you have a machine vision set up after coding with automatic guns in a booth to do robotic touch-up?
Yeah, absolutely. And going back to what Rob explained about the fact that our 3D technology can help our Omnibrain to see where are those faces that requires those touch-ups. The difference is that feature, that touch-up feature would require the user to provide the information where to apply powder to do those touch-ups. It's not like a closed loop system where we can use our 3D vision system to find where are the missing spots and then tell the robots where to go. If there was such a sensor that could exist, maybe we could integrate it to our technology. But for now, our sensing technology is really to create the 3D shape and position it in space. But then we can use all kinds of different behaviors, and part of that are the CAN model behaviors to find those faces on the actual part while it's coming inside the powder line, and then have the robot do the touch up. So there's a part of user knowledge that comes into place, where they know where they can expect the touch ups to happen, and which is usually the case. This is what we hear most of the time from the market. Users will say, well, I know these specific areas will require a touch up. So, can I have the tools to use the robots just for, just for these, for that function? And yes, it is possible.
Okay. Question here is, can a ultraviolet LED be attached to, call it the robotic arm, and using the same vision system for the curing, because that part to distance is critical for the UV cure? Have you seen that at all?
No, it's the first time that I've been that I'm that this type of application I hear about, but any type of application where the process is a spray process should be compatible with our technology. And for me, whether it's projecting a powder or projecting a laser beam or projecting a UV wave, I don't think there's that would make any difference for our technology. I think our technology could support it. Basically, we really aim on spray processes, and the main reason why is to be able to support the customers, basically line speed. We could, we could design or configure our system to, be able to process and treat, and use processes that require a higher precision, but that would require much more calculation time, from our Omnibrain, and therefore we might not be able to support a line that runs at, let's say, 10, 15. We even have customers asking us to test our system at 23 feet per minute. So it's a trade-off. We're trying to find the right balance between performance and precision, because our goal is that we don't want to require anything, any configuration or any programming offline. All the calculation have to be while the parts are on the line. So there's no programming required before the part is actually put on the line. So that gives a lot of flexibility for users. And yeah, so but the trade-off is on precision. But therefore, if it's a spray process, and again, if it's powder or if it's a light wave, for us it's still the same. Spray processes that our technology can support, definitely.
Okay. How fast is the mapping translation to movement, and what kind of line speeds are possible with complex parts and crowded racks?
So yeah, I get this question a lot, and really to define if the tech is able to support the line speed, it really depends on many on many factors, on many criteria. you could have a line speed that's fairly slow. I've seen that in in manufacturers of heavy equipment, such as agricultural or construction equipment. Their line moves obviously very slow, but their parts are fairly complex. They're complex welded assemblies. So that could generate as much computer processing load than a line that runs fairly simple sheet metal parts, but at higher speed. So so far, like I said, we have a customer that does, sheet metal parts, products based on sheet metal parts, and they're asking us to test our technology for speed up to 23 feet per minute. So far, we've been able to manage that speed, but the project is still on the engineering phase right now. But when we've also looked at projects where we're talking about complex complex shapes such as heavy equipment, and we've been also able to support, but these will run at less than 5 feet per minute. So it's a case by case, but what I just gave you as basic information should help pretty much everyone to figure out, okay, it should work for my. So I guess the best way to answer is also to contact us and provide that data, so we're able to give you a preliminary evaluation on if we can support the specific line speed.
Okay. And if somebody has an existing powder booth that where they spray through the doorways, openings type thing, can a robot be used in that type application by mounting on the outside and working through the window itself?
Yes, I have seen those types of application. It is possible. It's always a matter of positioning the robot is always a little bit of a challenge, because you want to give the robot as much room as possible to reach to all these faces, all these features that needs to get coated on the part. But on the other hand, if the robot has to work through a window, and of course I'm assuming that outside of that behind the robot, you would have the proper safety, whether it's safety fences or safety walls, safety measures installed. But it could be possible, and I've seen it. I've seen similar systems designed this way. The only issue that I see is you are limiting the the flexibility of the robot, because you're limiting the movement of the robot through a window. However, if your part size and different shape does not require more mobility or more flexibility from the robot, on our side, the digital twin technology that we use will allow us to recreate those constraints, those material constraints around the robot, to make sure that the robot doesn't hit that wall or an edge or anything that's collidable, and that we of course we must not touch. So that the digital twin technology is a great tool for constraining the robot. But on the other hand, that constraint can limit the capacity of the robot to reach all the surface of your part.
Okay. Can the system identify a part that only needs to be a coating on a certain area of the part, so it won't coat the entire part?
Yes, that is possible too. We have different methods to do that. It could be through a behavior. Behavior can be selected to find a specific feature, and then the user could basically assign a special task to that behavior, and say, well, the rest of the 3D shape that you have detected, I don't want the robot to process the rest of their surfaces. So that is possible. If for any reason, like Robert mentioned at some point, if there are hidden faces that must be reached, and they're, like I said, they're hidden, so the 3D scanning system cannot recreate them in the reconstructed shape. In that case, using the 3D CAN model, or a subset of the 3D CAN model. Actually, we don't use the entire CAD data file. We use a subset, which is, an STL is one of them. There's a PLI also format that we can also use. So these subset can be used to identify those faces, and and get the Omnibrain to figure out the robot motion to get to those surfaces only, and not the rest of the part if it's what the customer wants.
Okay. Well, does the system change any requirements for color changing? Is there, does it take more time or anything, or is that more predicated on the gun in the booth?
So the question is if the system can control the color change process. Is that it? Or
no? Does it, basically the time needed to make a color change, does it impact it?
Well, it can consider the time needed to do the color change for sure. I mean, the Omnibrain, well, our entire system works in conjunction with the line controllers. So line controllers can be PLCs, or nowadays they call them PACs, so programmable automation controllers. And it's basically that controller that basically reads what's happening, on the line, and tells the Omnibrain what to do. So the Omnibrain acts as a server. So if the controller, the line controller, tells tells the Omnibrain to wait because there's a color change cycle or process ongoing, and the line is stopped, or maybe the conveyor is not stopped, but there's no part that's going to come in because there's a color change process running. Well, the Omnibrain will just basically wait until the controller tells the Omnibrain to start scanning and start painting parts again. So since it acts as a server, and it needs to wait for those commands from the controller, from the line controller. That's color, whether it's color changing, regular maintenance, recovery from an emergency stop. Anything can happen on the physical line. Those situations and those input will be conveyed to the Omnibrain through a controller. So yeah, those controllers can be programmed to deal with all those situations and work in conjunction with the Omnibrain.
Okay. All right, that is the last of the questions that I have. So at this time, I would like to thank you both for joining us today. And I'd like to thank all of you attending the webinar itself. As mentioned before, don't forget to check out the Powder Coating Tough magazine, and join us in March 7th and 9th at Powder Coating Week in Orlando. Also, watch for a link to the survey, and just take a few moments to give us your feedback. Other than that, have a great rest of the day wherever you may live. Thank you.
Thank you everyone for attending.
Thank you.